All right, let's go over what's going on with class. So we're just a half a lecture behind, which is okay. We have some slop in the schedule, but because of that, I've moved some of the homework stuff. So we were going to be to homework 14, which was a drill tool path for SolidCam, but we're just starting SolidCam, so I had to move it till tomorrow. So technically, you have nothing due tomorrow. However, I'm warning you, we are now through our 8th day of class, and we only have 6 left. So do not take your foot off the accelerator. All these homeworks that are assigned to you already, you need to be working on them. You also need to be working on your SolidWorks final project. That's your personal project. And if you haven't done much on your SolidCam final project, you better get on it. So you need to be measuring the components that we have to build and modeling them in SolidWorks the best you can, because you're going to then need to take that and start machining them. I don't need drawings, just need part files and assembly files. Okay? Also, we're going to start today, we're going to put all this stuff in a box. Please make sure it gets back in the box. But we're going to put things like the gears and the motors and the potentiometers and the standoffs in the box. These are components that are purchased that you do not have to model, because we should already have models for them. So you can just drop them into your models. The components that you're going to build, you need to model. Now, Professor Hodgkinson started, I don't know if he's done, but he started dropping files in that you can use. So if we go to SolidCam Final Project, maybe he'll be here in here in a minute. He can show us where they are. But he's got part numbers so that you can go to McMaster-Carr or other websites and download the solid models of these pieces. So like these standoffs, they're already built, right? You don't have to model them. So he'll show us that in a minute. I am assigning one project today. It's not due tomorrow, it's due Friday. But that is and I've changed the calendar and re-uploaded it. That is, you need to square, drill, and ream your 1 by 1 by 1 cube and engrave the various marks. Okay? So if you'll remember on that cube, and if you want to, you can go look at some old examples or the example that you got to keep. You're basically replicating that part. So all you need to do is square. We have 2 dimensions done, and then you have a bandsawed side here. So you need to mill these sides nice and smooth and square to 1 inch long, and then you have to drill the various holes to the correct depth and at the right diameters. Remember, one of them is just drill it with a 1/4 inch drill. One of them is drill it and ream it 0.2500. One of them is drill it, ream it 0.249. One of them is drill it, ream it 0.251. It's all marked on your cube so you know, and we should have the drawing on D2L somewhere. So this is homework 13. You need to actually build that little guy. Now, you just turned yours in, so I'll have to grade these. I will grade these immediately after class because it's not going to take long, and then you can have your blocks back, say 5 minutes after class ends. Okay? Just give me 5 minutes to grade them. Are there any questions about that? Now, there's only 2 milling machines you're probably going to be able to use, which is the manual milling machine, and you can use Wolf Creek in the corner as a manual milling machine because it's a knee-style mill. So there's only 2 milling machines, so you've got to kind of coordinate with everybody else in the class. That's due Friday. I might have that due end of day Friday instead of start of day Friday, so that you have all Friday afternoon to complete that as well.
So can I add something to that? I didn't show you guys drilling and reaming on the machine. remember from my lectures, the spindle speed for the reamer relative to the spindle speed for the drill, what was it? Half or lower, really. So I didn't show you that, but try it out, and somebody will be around to help you if you need it. Okay.
And there'll probably be more lecture tomorrow, right?
Yes. I can actually show you a range hole tomorrow, first thing.
So let's make homework 13 do close of business rather than at the start of class. So you have till we close the shop on Friday. All right? Questions there? We need to know where you put those D2L files.
Let's see, SolidCam final project file. Yeah, look at the required parts. That should just be a simple document here. So it's just a text document, so you can open it here or whatever you want to do. The motor that we're using is at this website. So this is Pololu.com, a really cool robotics type website if you guys want to look around there. Do you want to go to that website there, Professor? That has a drawing of the motor. So you should be able to CAD up the motor. If you scroll down a little bit, scroll down, it might be on the specs, keep going, right here. So this gives you all the dimensions that you need to CAD up your motor. And we'll set another motor out on the workbench so you can see what the motor actually looks like. You could even take some measurements with that motor using calipers to make sure that these are correct values or somewhat correct values without taking the other motor off of the current assembled unit.
Pop quiz. What does this mean? Metric 3. So what kind of hole is this? It's a threaded hole. It's for a metric 3 millimeter screw. And what does 2 mean? There are 2 of them. Okay. Just throwing it out there.
Let's go back to the D2L real quick. Okay. So then the gears that we're using, these are the part numbers for the gears. So you could probably just copy and paste that into the Googler and it will pop up. Let's see if it does for you, sir. Click on the first one, I believe. I believe this will pull up a PDF. So you could either do this, or if you go back into the D2L, I have the PDFs for the gears that you want to use as the SDP_1. So I believe the SDP is the brand of these gears. So you'll have to find the gear here and the gear number in that column. And then the other column corresponds to the drawing up here for the gear that gives you the dimensions that you need for those gears. Okay, so you could fabricate this gear in SolidWorks yourself. There are easier options to do that, and I'll let you guys figure that out. This is the website for the company, sdp-si.com. So perhaps you want to go to that website and see if there's an easier way to get your CAD part. The other parts that you will need are the thrust bearing and the rotary bearings. Those are on McMaster card. Those are the part numbers. You can just copy and paste those into McMaster.com and you'll come up with the drawing files for those bearings.
Standoffs are also from McMaster. So you'll have to measure the standoff, figure out what size threads it is, and you can go to McMaster. The SolidWorks drawing is there. But you got to figure out which one it is. And the feet. The feet are also at McMaster. And there's a solid model for these. So don't forget, you're doing standoffs, all the various screws, the feet, this base plate, potentiometer mount plate, shaft coupling, that's at McMaster-Carr as well, this bearing block, this motor, these two gears, thrust bearing, this mounting plate, this axle shaft, these pillars. It's the whole thing. Okay? You guys are welcome to take this apart carefully. We're going to put it in a bin. Everything needs to stay in that bin. If you take it out and you mess with it, put it back. Okay?
Do you still have the PDF for those gears up? Maybe not. If you look at the solid part for the gears, or we'll actually put the gears out, the raw gears we get from the manufacturer, they will not have the holes, the mounting holes for this upper aluminum plate. So we'll have to add those in to your SolidWorks part, and then you'll have to actually drill and tap those holes on the physical gear. Okay?
Don't forget, we're going to take every part that you make and all the components that we bought, and to grade you, we're going to put it together and see how it works. So think of it in those terms. So you might want to be starting to put these things together to make sure it goes together right before you turn it in. You'll also have to engrave that ASEN 2003 with your proper unit number. We assigned those yesterday. I've got special end mills to do that, so real small end mills. So be ready. Questions? Don't put this off. We've only got 6 more days. Okay? I'm asking my employees about weekend hours. We may have weekend hours this weekend. If we do, they won't be like 8 hours. It'll be like maybe 3 or 4 or something like that. So we'll see. We'll see what we can do there. And if that works out and we need it, we'll probably do that next weekend too.
I may have missed this. Did you talk about where are we going to give them the solid model for the Arduino boards and the potentiometer?
I can. So the Arduino boards I got online, I can pop that up onto D2L. I'll do that under the SolidCam Final Project. Beware, it's a monster assembly. Whoever modeled it did a very, very thorough job. They modeled every single component on that board and then assembled it to the board. So it takes a while to open the file. So be careful with that. And then I could put the potentiometer on there. That's fine. Other questions? Don't put this off. Divide and conquer with the labor. You've got 2 or 3 people, so.
There's also an additional document on that part of D2L that will help you to position the gears, because we know that gears need to be a certain spacing apart in order for the teeth to mesh well. Yeah, I believe it's that one. So this picture will help you with the definitions that the PDF uses for different dimensions with regards to these gears. So the nomenclature essentially with gears.
What's really important to get these gears to operate together properly is this center to center distance. You see that? If that's off, the teeth won't mesh properly. So take a look at this drawing. Other questions about homework or anything like that? Okay. Let's continue with a little bit of solid camming. Oh, I didn't finish. So you're going to homework 13 is to finish off that little cube. I'm reminding you about your SolidWorks and SolidCam final projects. Just a reminder. You do need to watch 2 video tutorials for SolidCam. They're basically what we're doing today, so it'll be a refresher, but I'm going to go into a bit more detail. Those videos can be found by Googling SolidCam Jumpstart series, Jumpstart. And if you go to their website, you'll see these videos: create a new milling cam project and define the cam part. Those are the two I want you to watch. They're right here. Create a new milling cam project and define the cam part. And then I'd like you, once you're done with that, to create a cam part definition for one of the final project parts. So you're going to need to use, you can use the CNC to cut this plate or this plate, and maybe some of the other plates, but these are the best candidates. In fact, this bottom one's probably the best candidate, but you could do this one as well. So I want you to create a cam part definition off of these. Okay, and we'll go into some of that right now. Got that? I won't grade you on this one, but because you don't have enough information to get this done properly, but give it a try, please. All right. All right, let's look at the SolidCam environment. I'm all done if you want to bounce. We have the two SolidCam tabs, and I'd like to open a part. You'll see more when we open a part. You're probably not going to use this SolidCam part tab very often. What you will use a lot is this SolidCam operations tab. Okay, I'm going to open a file. This was a final project from last year. I made the final project a lot simpler, so you guys should be thanking me and all happy. No complaining. Where did it go, George? Well, it left, so let's I guess we'll just pick one of these. Bottom plate. Well, this confuses me. Okay. Sorry about this. I don't know where the files I wanted went. That is irritating. Well, let's just, I guess we'll just pick some here. All right, here's a plate. This was the floor of a CubeSat that we built last year, a 2U CubeSat. So I've got my SolidCam tabs, but I don't have a little SolidCam tab here. that has any kind of toolpaths on it. In order to do that, you need to go to the SolidCam in the window and go to New and pick the type of machining you're planning on doing. We're planning on using a milling machine. All right, this next interface is pretty critical. There's a big distinction here. You can create a CAM part either externally or internally. If you create the part externally, you will have two files that you need to transport every time you want to use them. So you'll have a star.sld.prt, that's your regular SolidWorks file, and then you'll have a star.prz file, and that's the toolpaths that you write. If you do it externally, it makes two of them. Then when you take these somewhere else to another computer, like at home, and you open them, you have to have both, or you won't get the toolpaths. Okay? Now there's advantages and disadvantages to this. This is external. If you pick internal, it's going to save the file as still as an SLD-PRT, but embedded within that file is going to be this PRZ. You just don't see it. PRZ. You just don't see it. Okay? If you try and open this on a machine that doesn't have SolidCam, it'll still open, but the toolpaths won't be there. They'll be grayed out and you can't mess with them. You'll see them, but you won't be able to mess with them. If you just open this one, you won't be able to see toolpaths at all. Now one issue here is if I write this file on this part and then I change this part, but I don't open this one's could freak out if changes were made here. If we wrote a toolpath on, say, a hole, to drill a hole, and then we changed this part without this open, it wouldn't update. So for that reason, we tend not to like externally defined parts. On the other hand, we've had some problems with internally defined parts. The SolidCam sometimes doesn't jive with the SolidWorks, and you can get goofy errors here, especially when you go to different machines. So each of them has their quirks. We are going to recommend that you do internal parts, but you can pick either. Okay? So I'm going to pick internal. And then it asked, what do you want to call the CAM part name? I'm just going to call it this same part name and underscore milling. That's what it said. And it asks where the bottom or the original SolidWorks part is also. So make sure that's the correct SolidWorks part. It usually defaults properly. This is going to be key here, is getting your units right. If you pick metric now, the units are going to be metric forever and you can't change it. I know that sucks, but it's the way it is. So it's very important that you get on the inch units because our machines are in inches and everything we measure is in inches. You must do it here. Notice that this is grayed out, but it's selected on inch. What can happen, I'm going to cancel, is it takes the default document units and puts it in those units. So if I go to, let me open that same part again. If I'm in millimeters and I do a new SolidCam, well, it didn't do it this time, but when I'm in external, I can select. If it was in metric, you need to make sure you go to inch. Oh, there it is. I clicked internal and it went to metric and it doesn't let me change it. Why? Because my document units are in metric. So for the time being, when you're writing toolpaths, change your units to inches, only because our machines are in inches. You won't be able to go back and change it. That's important. So select internal and inch and hit OK. Notice a new tab drops in the feature tree. That's your SolidCam tab, and it's going to have all your toolpaths in it. But for right now, we're working on the property manager, and SolidCam is asking for a bunch of properties that we care about. You have to set this up properly. This is called creating the CAM part definition, and that'll be on that video tonight as well. First thing is the machine. You must select the right machine. So if I was working on the big bed type mills, I'd use Centroid. If I'm working in the corner on Wolf Creek, I would use Accuray. Let's pick Centroid. The next step is coordinate system. We have stock and target, and that's about all we need to do. We need the machine, the coordinate system, the stock, and the target. You can mess with some of the other things, but it's not really necessary at this point. Coordinate system is very important. Okay, let's go ahead and define one. Let's hit define. There's a lot of options for how you can select the coordinate system. You can define it yourself. You can select coordinates. You can do normal to places. The most common is to select a face. We bolt this down to the table with this face showing up. So I'm going to select that face. Remember, the head comes down and machines on the part. So typically you want to select the face that's normal to the head. Alright, so I selected the face. SolidCam does what SolidWorks does, and it tries to guess what you're after. Sometimes that's good, sometimes that's bad. Alright, it also automatically dropped in a green, red, blue coordinate system that matches the colors of the SolidWorks coordinate system. I don't want mine there, so I'm going to pick it somewhere else. So now that I see it, I'm going to hit pick and hit pick origin. Alright, I'm going to pick up here just for now, but I'm actually going to come back and change this in a second. I'll show you why. What you need to make sure of is that the orientation is correct. If I was clamped on the table this way with my X travel going this way, this coordinate system is not correct right now. Notice red is X. So that would be the way I'm looking at it now. My milling machine table is like this, right? The way I'm looking at it now, this part is going to be like this. You see that? Because see the notches axis? I'll put it here. Here's that notches axis. That is parallel to the X axis here, the red one. If you don't like that, you need to flip it around to where you want. In this case, this is the Z axis. I'd want to rotate about Z, so I flip around Z. Now I've got my X axis this way, my Y axis this way, and my Z coming up out normal to the plate. This is correct for what I want. I'll accept that. Now you get a coordinate system data tab. We're going to go into this in more detail later, but the machine coordinate system number will generate a G code. In this case, it was G54. That is the standard coordinate system for our machines. You guys are going to have to use different coordinate systems. You're going to have to be careful. Let's say on copper, we have 3 groups on copper, right? One of you is going to have to be on system G54 or machine coordinate system 1. One of you is going to have to be on G55 or 2. And one's going to have to be on G56 or 3. Because you're all going to have different origins. Right? Those are called work coordinate systems. So you're going to have to be careful too. If these guys come in and work on G54 and then these guys come in and they start changing zeros and forget to go to G55, they're going to hose these guys as zeros. So be careful. All right? Those are work coordinate systems. We'll go into more detail later. But this is where you find it in SolidCam, the machine coordinate system number. All right, this is a global system for levels. Tool start level is at every different tool path. It's how high off the part the tool is going to start. This is at 5 inches right now. The clearance level is, if I drill this hole and I want to go to drill this hole with the same tool, the clearance level is the height at which the tool is going to come up to before it goes to that next hole. So the start level is the start of the program, 5 inches. Then it comes over here, drills this hole, only goes up to the clearance level, which currently is 1, before it moves to the next hole. You need to be careful with this, because if there is a clamp right here, you need to come up high enough to move over the clamp. Otherwise, it's going to blow right through the clamp. Okay? So in this case, I like to pick something higher, say 5, for a global parameter. Yes?
Is that level, is that the height above, or is that your z-axis height? Or
That's
is that
right.
the height above the...
Z-axis height above the part.
So from the origin or above the tallest point of your part?
From the origin. From the origin. So you have to be careful where you define your origins on your parts. Okay? That's assuming that my part upper level is 0 and my part lower level is a negative number. I like to define my parts that way. I like my upper level to be 0 and everything below that to be negative and everything above that to be positive. Why? Because at a quick glance at the controller, if I see positive numbers, I know I'm good, okay, safe. I'm not cutting in the material. If I'm below the surface, the number says a negative, I know I'm bad, I'm in the material, I'm potentially in trouble, I'm cutting material. So that's the way I like to define it. You could define it a different way, but you need to be careful. If you define your 0 down here, and then you don't make your upper level high enough, you might be dragging through material every time it moves. So I like to define it this way. You can actually hard code these numbers, or you can click the button and select the upper level. Z0, part lower level, flip it over. I want it here, accept. SolidCam kind of guessed that's what I want based on this part. It's a pretty simple part. All right, I'll hit OK. I now have on machine coordinate system 1, Mac 1, I have a coordinate system. Accept, and now this coordinate system is done. We will move into stock and target starting tomorrow. So give me a few minutes to grade your homework 11s, and then you can have them back and you can start working on them as soon as now. Otherwise, we will see you tomorrow.